All right. On the other hand, we could look at this in terms of Avogadros. What does Avogadros say about this? So let me do that up here. So in terms of Avogadros, when we look at this mixture, okay, the first thing is how many liters of nitrogen do I have? If I consider this an Avogadros mixture, how many liters of nitrogen are there? 0.8. And so I have 0.8 liters of nitrogen. And how many liters of oxygen would I have? Yeah, 0.2 liters of oxygen. Now, if I put all those molecules into a smaller box, here the pressure should go up, of course. This is a 20% smaller box. Put that in there, but now we don't have the oxygens. The oxygens are in a separate box. Here. And so what is the pressure over here? Yeah. The pressure of nitrogen, we're going to have 1.0 atmospheres. Actually, I need a little bit of room here. This is the volume of nitrogen. This is the pressure of nitrogen. And so this is 1.0 atmospheres. The pressure of oxygen is going to be what? 1.0 atmospheres, right? And so when I add these up, I added the avogadros, and I get V total, which is going to be equal to 1.0 liters. And so, in other words, Avogadro's law just says that the total volume is the sum of the partial volumes. The volume of A plus the volume of B plus dot, dot, dot. However many gases we have in there. However, the pressures, are not. The pressures, P total, well, what's the total pressure? Total pressure is 1 atmosphere. What's the partial pressures? They're all 1 atmosphere. And so P total is equal to P total is basically equal to the partial pressure of, nitrogen, which is equal to the partial pressure of oxygen, dot, dot, dot. Well, we only have 2 components here. That would be it. But anyway, P total is equal to PA, which is equal to PB, which is equal to PC. And so this is Avogadro's. This is Dalton's law here. Okay, so here we're visualizing in terms of Dalton's. Here we're visualizing in terms of Avogadro's. Here. Well, it makes a difference. It's the same mixture, right? This is air. But what pressure and what volume we use depends on how we visualize the mixture. And so if I was to do a calculation, let's look at this. Let's say I want to calculate how many moles of O2 I have in the mixture. Then in order to figure out the moles of O2, I need the pressure of the O2 times the volume of the O2 divided by RT. Now here it makes a difference, right? Here I don't want to mix things up. It's easy to get things mixed up. And so on the one hand, I have 2 choices for this. If I visualize this as Dalton's, then what's the pressure of the O2? 0.2 atmospheres. And the volume? 1.0 liters. If I visualize this Avogadro's, then what's the pressure? And the volume? I'm going to get the same answer, of course, because it is the same mixture. But the problem happens when people don't keep track. Because sometimes the information in the problem is presented to you in Avogadro's, but you take it as Dalton's. And then you get them mixed up. So what happens, the most common error is somebody will use let's say the Dalton's pressure with the Avogadro's volume, then are you going to get the same answer? No, or vice versa. And so that's frequently an easy place to make a mistake. It is very easy to make a mistake in gas mixtures because the emphasis has always been on Daltons, you know, especially in Chem 4. Did you really do much with Avogadros? Maybe not. But a lot of problems, especially in chapter 7, are going to be Avogadros style mixtures, not Dalton style mixtures. And so, you know, when you're dealing with an Avogadro, somebody asks, oh, what's the pressure, the total pressure? Well, you know, we're dealing with an Avogadro mixture, and you ask, what's the total pressure? Well, the total pressure is, oh, I know what the total pressure is here. The total pressure is 2.0 atmospheres. Do you see how easy it is to make that mistake? Pressure of the nitrogen, oh, these are the partial pressures. You just add the partial pressures to get the total pressure, but that is wrong. It's wrong. And so we have to be comfortable with both ways of visualizing gas mixtures. And so let's summarize that here. So if we have a mixture of air, which is 20% oxygen, 80% nitrogen, then this is the way we can think about it here. So let's look at the oxygen first. Oxygen, in terms of moles, you know, Na over N total is just going to equal the number of moles of oxygen over the total moles, which is going to equal 20 out of 100. Right? That's the mole fraction. But is it also true that you know, that this is equal to the pressure fraction? So, for example, the partial pressure. So in terms of Dalton's, the partial pressure would be 0.2 atmospheres, the total pressure 1 atmosphere. So 0.2 over 1 is the same as 20 over 100. And so, you know, the mole fraction is the same as the pressure fraction. But is it also true that the pressure fraction is the same as the volume fraction? Because, well, it depends on what method you use to look at this. For example, if we're talking about Dalton's, then, yeah, the pressure is 0.2 over 1, or 20 out of 100, right? And if you look at this in terms of Dalton's, then the volume of oxygen is 1 liter, and the total volume is 1 liter. So this is false, right? In terms of Dalton's. This would be true in terms of Avogadro's, because in terms of Avogadro's, the volume is 0.2 liters, and the total is 1 liter, so that's 20 out of 100. But in terms of Avogadro's, then the pressure is 1 atmosphere over 1 atmosphere, and this would be false. And so we generate an equation like this. This is always true. And so Na over N total is true regardless of pressure or volume. And so we just say always true. Okay, this ratio will be the same for the pressures if we're looking at it in terms of Daltons. And in terms of Daltons, the volume is fixed. The volume is constant, so everything has the same volume. This would be Daltons. But we also get the same mole fraction, or the same fraction in terms of volume. And so the volume fraction is the same, but these two cannot simultaneously be equal. Because for the volume fraction equal the mole fraction, the pressure is constant. In other words, we're looking at this in terms of Avogadros. And this is equal to a symbol we call chi A. Chi is called the mole fraction. So we end up with this equation here. Well, we'll go on. Oops. Check something really quick.